Okay, so once again we have the functions y is equal to the square root of x, y is equal to 0, and x is equal to 6. And this time we were looking at determining the volume about the y-axis. Okay, so we have for the graphs of these three functions, again we have the vertical line x is equal to 6, horizontal line y is equal to 0, and of course the radical y is equal to the square root of x. And again we're looking at determining the volume about the y-axis, and for what we have in this particular situation is that we're going to be looking at integrating over y, and for what we have here, if you integrate over y, we'll be looking at a sideways perspective where we have x is equal to 6 is to the right of y is equal to the square root of x, and to make all the terms integrable over y, we need to rewrite our radical function in terms of x equals. And so we have transformed from y is equal to the square root of x, we have x equal to y squared. And again for the key points, we have the origin, and we have 6, 0 once again, and then we have in the upper right hand corner region we have 6 and the square root of 6. And again, so we have x equal to the quadratic term y squared, then we have x equal to 6, and we have y is equal to 0, and again you'll be looking at integrating over y. And with the nature of the graph itself, past the point of origin, there is no kind of contact between this graph and the y-axis, so you will have a perpetual hollowing out. And so this is an indicator that once we cross over to determining volume, we will be working with the method of washers. And so in terms of writing what we have in radius terms, again we're looking at for the radius, you have an open section, and the nearest that the region will get to the y-axis is going to be dependent upon the inside radius, where we have that r is equal to y squared. And in terms of the outside radius, this is derived from x is equal to 6, so the maximum radius is going to be at 6, and so that is going to be the outside. And for what we have in terms of the setup and illustrating the solid that is going to be formed, you have in this one, this will be rounded at the top and the bottom and hollowed out in between. And what I did in advance was to take, visually speaking, a washer out, and we have with this section, we have the inside radius, again it's going to be at y squared, and then we have for the outside radius, we have that equal to 6. And to let me there we go. So you have r is equal to y squared, and in terms of the outside radius, that is going to be at 6. And setting this up where we can integrate, we have in the setup, we have that v of y is equal to pi times the outside radius minus pi times the square of the inside radius, integrating over y. And just to reiterate, integrating over y, we are going from at the base y is equal to 0 to the utmost level of y, which is going to be at the square root of 6. And so we have going from 0 to the square root of 6, and taking the squares of 6 and y squared, we have in the next round, it follows that we have v of y is equal to the integral going from 0 to the square root of 6 of 36 pi minus pi times y to the 4th dy. And as we carry out the terms and look at using the power rule of integration, what is going to follow is that in this one, we have 36 pi y minus pi times y to the 5th over 5 as y proceeds from 0 to the square root of 6. And as we look at substitution of the square root of 6 into y, now the lower limit 0 is going to render the expression negligible. So with the upper limit we have 36 pi times the square root of 6 minus what is going to be the term or the expression 36 pi times the square root of 6 over 5, And as we combine the terms together, it is going to end up where the volume of the solid generated about the y-axis is going to have an exact value of 144 pi times the square root of 6 all over 5.